Okay, if not, let me start. So today we are going to look at directed graphs. In fact, we will spend very little time on directed graphs, maybe like a couple of lectures. And later point, we will see if we want to use visit more of this. So what are directed graphs? Directed graphs basically represent when when the relation that we are talking about is not symmetric. Right? For example, if we are saying that the network is or the graph is going to represent x, if there's an x between 2 points, then there is a communication line between them. You are saying that there is only one way communication, or if you are saying that the traffic network, then you can say that the traffic has a direction, right? Like so situations like that, if you want to represent, we will use directed graphs where we use graphs with some kind of orientation, and it can have both bidirectional edges, like where you have u to v there is an edge, and also v to u there is an edge. Something like that is also okay. So already done this. So a directed graph is basically a pair, let's say D, right? We call it by D instead of D, equal to VA, where V is the set of vertices, and A is the set of arcs, which are basically ordered tuples or ordered pairs of vertices of the graph. So ordered pair means that there is an order, right? It says that if AB is an ordered pair in the arc set, then you are saying that A to B the traffic is positive, right? Or like A is the father of B or something like that, some relation. Now some examples so you start with set 1, 2, 3, 4, 5 as the vertex set, and then you define the arc set to be the pairs that we want include, like 1, 3, 3, 4, 2, 1, 2, 4, 4, 5, and 5, 4. So these are the arcs, and then we have the direct. So you will see that 4, 5, and 5, 4, right? Both can appear in some cases, but in some cases it may not be there. For example, 2, 4 is there, but 4, 2 is not. Now, so such graphs, how do you represent in terms of in the diagrams that we use, right? The graph pictorially, how do you represent it? Again with the arrows. Okay, so when you say that 2, 4 is an edge, you can say put 2 to 4 there is an edge. So here is another example. You have a 6 vertex graph, and the arcs are as follows, like 1, 2. So 1 to 2 there is an arc. Then 1, 3. So 1 to 1 to 3 there is an arc. Okay. Then 2, 4. 2 to 4 there is an arc. So like that, 4 to 1 and all this. So all the directions are marked by the arrows. And because 3, 4 and 4, 3 are both pairs appearing, you have these two going in both directions. So that is the graph. Now what is the another couple of examples here. So I have just drawn two more graphs where like all pairs of the edges, arcs are there. It has the corresponding arc to go backwards. So this graph actually represents bidirectional traffic, right? You can go from any vertex to its neighbor. If AD there is an arc, then DA also there is an arc. Okay? So in fact, in this first graph, you can actually represent most of the things. Like, of course, in certain cases it may be different, If you have weighted graphs, it will be different. But if you are looking at unweighted graphs, then you can as well say that, okay, this is basically representing an undirected graph, right? Because both directions are possible, right? So if you are just talking about the relation, it's basically symmetric. But if you have a weighted graph, it could be different. So we'll come to that maybe later. And here are so if you look at three vertex digraphs which have exactly three edges, one can verify that these are the only graphs up to isomorphism. So, but I have not defined what is isomorphism. So let me see what is isomorphism. We'll define it in the next page. So now we can talk about the degrees. So what are the degrees? So since we have these arcs like in two directions, we define three notions of degree. So one is called the out degree, where the number of arcs which goes out of the vertex, right? So which has the starting vertex as v, and and then some other vertex possibly as the end vertex. So this kind of arcs are called the out edges, and then the number of such out edges, right? These are the out edges. Will tell you this is the out degree of the. So basically, the out degree is the set of all y such that out degree of the vertex x is the set of all y such that xy is an arc, and it is denoted by d plus of x. So say that the out degree. And d plus of the vertex v in this example is 3 because we have these 3 outgoing edges. Similarly, the in degree is the number of incoming edges. So incoming edges are the set of all y such that yx belongs to a, right, for the vertex x, and is denoted by d minus, and the d minus of v here is 2. There are 2 incoming edges here, incoming arcs. And the degree of the vertex is the sum of the out degree and in degree. That is basically the number of edges incident, right, or number of arcs incident. In many books they use the same term like edge for the arcs as well as the edges of the graph, which is also fine as far as we understand that the context we are talking about is clear. But when you have some questions regarding this, we better use R to represent the direction. Now, the that set of vertices to which there is an arc from x is called the out neighbors of x, and the set of vertices from which there is an arc to x is called the in neighbors of the vertex. So if x to y is an arc, then y is an out neighbor of x, and x is an in neighbor of. And first theorem of digraph theory is basically given a digraph of m edges, m arcs. Right? The size is basically the number of arcs. So the number of arcs is m. Then the summation over all the vertices d plus of v is equal to summation over all the vertices d minus of v is equal to. This is like immediately clear intuitively, but you can write a proof, just one line proof. So I will leave it as a exercise. Now, one can also have loops. As we said, we already have multiple edges, right? Like parallel edges are basically multi edges in the base graph that we are looking at, right? So, but we can also have loops, and the loop. Now, if you look at the degree, right, of a vertex, that degree is the sum of the in degree and out degree. But when you have a loop at a vertex, its out degree is 1 and its in degree is also. So the sum of these two is going to be 2. So the degree is 2. So this is why many cases in the when you are looking at the undirected graphs also, the loop contributes 2 to the degree. But of course, then there are there are some cases where we will consider it as only the number of edges incident, and then in that case we can also consider it as one. So this will be very clearly mentioned, I think, when we people discuss what how it is, loops are there, how do you count the degree is important. Okay. Now here is the definition of isomorphism. So a digraph, let's say D1 and D2 are given. We say that D1 is isomorphic to D2 if you can find a bijection from the vertex set of D1 to vertex set of D2, such that UV is an arc of D1 if and only if phi of U, phi of V is an arc of D2. This is the normal extension of the definition. And then phi is called phi is called anisomorphism between these two graphs. So there could be several isomorphisms. So we have to talk about anisomorphism. Now, so as I mentioned before, like these are the non-isomorphic digraphs with the 3 vertices and 3 edges or 3 arcs. So one can verify that these are the only 4 of them. Now, as so we will go slightly fast here because we are just discussing the same notion that we have discussed before. With just the only difference is that you have the arcs instead of the bidirectional edges. Right? So given a digraph D, we say that the sequence of vertices V1, V2, etc. Vk is a directed walk. If for each I less than k, Vi plus 1 is an arc, right? And essentially we are saying that so just as in the terms of walk in a graph, now you have the sequence which are edges, but now the arc must be in the correct direction. That's all we are saying. A directed path is essentially a directed walk where no vertex is repeated. Yeah, so here is an example like graph. Here. So this is basically a directed walk from the vertex, let's say 1 to vertex 7, right? So this is a directed walk, but it is not a directed path because the vertex 1 is repeating, right? On the other hand, if you have, let us say, to this and then going to 1 and then coming to 7. This is basically a directed walk because no vertex is repeated, and you can see that it's basically like a walk, but the arcs are in the correct orientation. On the other hand, if you are looking at you are looking at a walk where you go from go from let's say 7 to this direction, right? This is not going to be a directed walk because you are not allowed to go in this direction because the arcs are only going in the other direction. Therefore, this is not a walk. So we want the arcs, all the arcs to be in the correct orientation, right? And a directed cycle is essentially, if you take a directed walk and then, from U to V, then if VU edge is also there, then together with the edge, it forms a directed cycle. Right? So it's all the extension of our definition for undirected. We talk about directed graphs. We mentioned that we allow edges or arcs from U to V as well as V to U, right? Because sometimes it could be symmetric that both directional edges may be present. But if that is not the case, right, then we say the graph is basically an oriented graph. So oriented graph is basically you take a simple undirected graph, right? Take a graph, and then you just give orientation to the edges, right? So you say that okay, pick each edge and say that okay, this edge is now a directed edge, right? So I will say that okay, if UV is an edge, then I will say either it is U comma V is going to be in the R set or V comma U is going to be, and we don't put both of them. So this way we will get a directed graph which is called an oriented graph. So oriented graph, we know that there are no two cycles. So two cycles. So this is a two cycle in the graph because you have y, let's say, so xy arc and yx arc. So if such structures are present, then it's called two cycles, and two cycles are not present. Then of course loops are also not there. Then we get an oriented graph. So this is called yeah. So this is basically our oriented. Now a tournament is basically the orientation of the complete graph. So you take the complete graph on any n number of vertices for any n, right? And then take its edges and then give some orientation, whichever way you want, right? So then you get what is called a tournament. So here there is a three vertex tournament T3, right? I mean, but you can have other three vertex tournaments, right? Which are not isomorphic to it. Right? For example, here I have the property that this going from 1 to 3, right? 1 to 2, 2 to 3, and then it is 1 to 3. There is no directed cycle, but I can also orient it such that there is a directed cycle, right? So therefore, these two are going to be different tournaments. So similarly, you can have different orientations for each of these, and you will get different tournaments. So given a complete graph, you give orientation to its edges, then we get what's called a tournament. So it's called a tournament because it's like you have n players playing some game, right? Then every two of them plays against each other, right? And then one of them wins, right? We will say that we'll assume that there is no draw, right? One of them wins and then the other loses, right? So we can now represent this as the directed edges, right? So if U is going to beat B, then you can say UV is an arc, something like that. Now, given a directed graph, right, or digraph, we can also look at the graph, that is obtained by the looking discarding the direction, right? So I will just consider these arcs as edges, and then what I get is basically called the underlying graph of the diagram. Now, if in some cases we will only the consider the simple graphs as the underlying graph, but in some cases one can look at the multiple edges also. So, but for the time being, we will assume that we will discard the multiple edges and orientation. So even if you have two directions edges, we will still consider. Even if we have bidirectional edges in this case, we can still consider this graph as the base graph. So this is the definition that we are going to use at the moment. Now, so we have given a diagram. We can talk about the underlying graph. Sometimes it is useful, to look at this underlying graph. We will see why. And this example that you have. Now, let us talk about a diagram being connected. Right? So, in fact, again, here there is more than one notion of connectedness. Right? How we look at the graph as connected. So, of course, the first graph. Okay, I have not put any orientations. So, the first diagram is. Of course, just looking at it, we know that it is not connected, right? So it's disconnected. Now, if you look at the second graph here, right? What can you see in this graph? If you look at this graph, you will see that the underlying graph is connected, right? The underlying graph is connected, and but if I want to go from let's say vertex number vertex 5 to let's say vertex 3, right? So if I want to go from 5 to 3, I am actually not able to reach from 5 to 3, right? Because 5 out of 5 there is no arc going out of 5, or there is no arc coming into 5 into 3, right? So therefore I cannot find a directed walk from 5 to 3. So the underlying graph is connected, but the diagram has this vague notion of being connected. I mean, it becomes a little more vague, right? Like, what do you mean by being connected? That we want reachability from any vertex to any other vertex, then of course this one is not connected. Now, on the other hand, if you look at the third graph, right? So the third graph again, you still won't be able. You can go from let's say 3 to 4, 2, right? So I can go from 3 to 1, 1 to 3, like 2 to 3, 2 to 4, all these things I can go, right? Similarly, I can go from 1, not 1, let's say 7, 9, and 6, right? So 6, 7, 8, 9, I can go between them. I can go from 4 to, let's say this one is 8. 8 I have. 10 I can go. But I cannot go from 10 to 4, right? Because 10 out of 10 I cannot go anywhere. So here things are slightly better than the previous one. If you look at the previous one, you will see that it is much more less connected in some sense. So we will define why what is different about that. And then if you look at the last one example, the fourth example, you will see that from any vertex to any other vertex you can go. You want to go from 7, right? you can go like this. 7 to 1, I can go like this. Similarly, this cycle you can go anywhere. This cycle you can go anywhere. This cycle you can go anywhere. And once you reach one of these, you can reach any of other vertices. So you will see that this digraph between any pair of vertices, I have a walk, right? Okay. So here we define formally, this concept. So a digraph is said to be weakly connected if its underlying graph is connected. So we have two notions of connectivity here. Like one is said to be weakly connected, which means that except for the first one, all the three are weakly connected. The underlying graph connected. Now digraph is strongly connected if UV, right? In fact, every pair of if you're talking about every pair of vertices, then you have a UV walk as well as a VU walk, or UV path and VU path, because if there is a directed walk, there is also a directed path. So a digraph is strongly connected if I can go from any vertex to any other. So in this example, the fourth graph is the only strongly connected graph. So the digraph that is strongly connected is the fourth one, right? This one is not strongly connected, but it is weakly connected. This one is also weakly connected. But there is some difference between the second one and third one, in the sense that if you look at the third one, there are directed cycles, right? Because 2 for 1, 2, 3 for 1 is a directed cycle, and there is another directed cycle, 8, 9, 6, 7, right? But the second graph does not have any directed cycle at all. So you can verify that there is no cycle is directed cycle in this, and this is this kind of directed graphs are called directed acyclic graphs. We will look at that sometime later. Okay, again, some examples. The first one is not connected. Second one is directed acyclic graph. The third one is weakly connected. This is also weakly connected, but it has some directed cycle. And the fourth one is strongly connected. Any pair of vertices you can go. And directed acyclic graph is basically a directed graph with no directed cycles. Okay? So it's sometimes called DAG, DAG. In some books, you will just they will define it, of course, somewhere, but they talk about DAGs. So DAG is basically directed acyclic graph. So we always talk about some, right? So you can always find some some orientation where the graph becomes directed acyclic. So can you prove that every graph has an orientation which results in a directed acyclic graph, right? Some orientation. So this will be a nice question to think about. How do you do that? Not so easy to solve, maybe, right? But it would be nice to think about these things. And some people, and we don't know, like sometimes very simple ideas will solve a very long-standing difficult conjecture, some difficult looking conjecture. And there was a recent example, like at least around 4 years back, a conjecture which was standing open for like something like 40, 50 years was resolved by a very young mathematician called Zivdur. And in a less than a page length proof. In fact, a half of page length proof. So and using very simple tools also. Not, but you have to get the right idea. So sometimes you might think that it may be difficult because so many people have tried, but you get the right idea, you might be able to solve it. So if you get any ideas on any of the conjectures that I state, let me know. We will see how it is. Okay, so here is a conjecture. Before the statement, let me define a few more things. So given a digraph D and a vertex V, we look at the set of out neighbors, right? Is the vertices to which there is an arc starting from the vertex V, right? So the set of out neighbors is denoted by, let's say, n plus V. And if you look at the set of vertices which are at distance 2 from the vertex, then we say it is n plus plus. Okay? So if you look at this, of 1, 2, and 3, 4, 2, and 3. So basically, n plus of 1 is 1, 3, and 4. I mean 2, 3, and 4, right? Yeah. But what is n plus plus of 1, right? N plus plus of 1 is okay. So 1 to 4, there is a directed walk of length, right? I mean like 1 to 2 and 2 to 4. But that is not the distance from 1 to 4, right? Because 1 to 4, there is a direct edge. So the distance is only 1. So we don't consider 4 as, an element of n plus plus of it, right? So it is not included. Therefore, what about 3? Of course, 3, I can go from 1 to 3 directly again. So 1 to 4 and 4 to 3, even though there is a walk, 3 is also not in n plus 1. And what about 2? To 2, there is only distance 1, but there is no other walk also. So 2 is also not there. So it is basically empty set. But what about the n plus of 2, right? N plus plus 2. Well, 2 to 3, there is no R, but 2 to 4 and 4 to 3, there is a 2 R. So therefore, 3 is at distance 2. So therefore, this contains the vertex 3, and anything else, in fact, nothing else, right? So this singleton 3. So n plus plus is the set of vertices distance 2 from V by a directed path of length 2, and n plus would be the set of out neighbors. And yeah, more examples here. So in the first graph, n plus of V is 1, 2. It's 1 and 2 are out neighbors. N plus. Now, if you look at the out neighbors of the vertex, that is another thing, right? So if you look at the out neighbors of the out neighbors, of course it will contain 2 and 3. But if you look at n plus plus of V, where we are looking at the distance 2 neighbors, then it contains only 3. Right? Because to 2 also there is a directed walk like V to 1 and 1 to 2. So therefore 2 is also in the n plus of V, but it is not in n plus plus. So you should see the distinction between this and this. And again another example with this thing. I have not completed this. You can complete this and see if there is any more or not. Now, if you look at this digraph with the cycle of length 2, right? For the vertex, let's say u or v, right? If you look at the n plus of v, it is u, right? Singleton u, and n plus plus of v is empty set, right? And similarly, n plus of u is singleton v, and n plus plus of v is empty set. But now, people observe that this. Suppose we are looking at oriented graphs where we don't have, directed to two cycles. Then one can find some vertex, right? Whose so in this case, you know that the n plus of v has the one element and n plus of v is empty, right? So the cardinality of n plus of v is strictly greater than the cardinality of n plus of v. But if you don't allow directed cycles, a conjecture due to Seymour says that you will always find some vertex. You will find some vertex, not for every vertex. You will find some vertex whose second neighborhood is at least as big as the first neighborhood. So this is called Seymour second neighborhood. So given a directed graph, which is an oriented graph, then this graph has some vertex x such that its second neighborhood, which is n plus of x, is at least as big as the first neighborhood, which is n plus of x. Now, this result is, this conjecture is proved for the tournaments that we are talking, right? So, given a complete graph and then you just give orientation, what you get is an oriented graph. It's called tournament. So, for tournaments, people have shown that this is indeed true. But for general, oriented graphs, we still don't know. Okay? So it is still an open question. It was proved by Fisher, I think, in 1996. The conjecture is true for case when the direct graph is a tournament. Okay, so we are now going to look at what is called network flows. It's a it's a topic which basically grew out of some practical questions independently of graph theory. So there were several results which have been proved in graph theory in parallel with the theory of network flows. And so the flow theory is another topic itself. But many of the results in both of these are parallel to each other. And essentially the same ideas because they were working, separately in separate places and separate groups, and there was not much of communication, right? Till some point, and when people realize that okay, we are doing the same work, duplicating in places. But of course, the way the approach to the questions can be different, and sometimes the ideas that has been developed in the theory of network flows can be very useful in graph theory, and vice versa. So we will take a very quick look at network flows. So what's a network? A network is essentially a digraph, but it has two distinguished vertices called the source and the sink. So the network basically represents either communication or transportation, things like this, where you have, let's say, you are looking at transportation network. You have a factory which produces things, right? Many products, and then you are sending these products to, let's say, the terminus where you are going to export it to something, right? So you want to send these things, but now there could be several road networks which will allow you to take the let's say you are taking all these materials in let's say trucks, and right, so you are taking using the trucks, and then you have several roads possible. Now these roads all might have like some conditions, like for example, in one of the roads maybe there is a bridge where whose weight capacity is limited, say 5 ton, right? So you cannot put very large trucks to go through that, right? So which means that is essentially limited by the capacity, right? How much material can be transported is essentially limited by the capacity of the bridge. Similarly, each road has its own bridges and capacities maybe, right? Or even the traffic might make you use a less number of trucks in a given route, right? So we want to use as many routes as possible, which minimizes the maybe the cost of transportation, or like maximizes the capacity. Uh, you know that we can basically you want to take as many things as possible to the the terminus, and you can send it to, right? So this is the idea. And so therefore these kind of questions, like optimization questions, naturally come. So again, what is the network? It's basically a digraph with two distinguished vertices, S and T. S is called the source, T is called the terminus or sink, together with a non-negative real valued weight function. It's called the capacity function. Okay, it's denoted by C. So we have basically an edge weighted or arc weighted diagram with two distinguished vertices, where the first vertex, things go out of it to other places, right? And the last vertex receives the material that is sent from the source. So here is an example, right? A very simple example of a network. So we have the source here and the sink here. And somehow my pen is not working very well today. So we have the source here and the sink here, and you have this directed edges, and the numbers on the edges represent the capacity, the maximum amount that can be transported along that direction. That is the maximum capacity. I mean, this could be very well a communication network where like uh, the bandwidth of the line, right, can be basically represented by the capacity, right? If you have a 10 Mbps line, you cannot hope to have more data transferred through that line, right? So because it is the capacity is constrained by the 10 Mbps limit. So yeah, so now if you are looking at the vertices other than the source and sink, right, they are called the intermediate vertices of the network. So these vertices U and V are intermediate vertices, and the source and sink are special vertices. Here is another network, and you have again a source and sink, and you have the capacities, and you have the directions in which we can transport things. Now, the idea is to basically find the maximum amount of things that can be transferred from S to T. Now, how do you do that? For that, what we do is that we want to assign like what we are going to transport to this. See, the main problem is that suppose I am going to send, let's say, so I can send 5 units from here, right, through this arc, through this arc, and 4 units through this arc, right? Now, let us say that I send the 5 units here, right? Now, where do I send this 5 units from here? Well, this one only takes care, at most 4 units, right? So 4 units can go from here, but this 5 must be like see, if I send 5 from here to here, it should somehow reach T, right? If it doesn't reach T, then it's basically a waste. This product will get lost, right? So if I'm sending 5 through here, I should make sure that 5 also goes out of this vertex, intermediate vertex. I don't want anything to be lost in intermediate vertex, right? So what I want to make sure is that whatever goes into an intermediate vertex always comes out. Now you will see that if I go from S to this vertex, right, using, if you take all the 4 here, then this 4 can never go out of it, because the only outgoing arc from here will take only 3, right? So I should never send 4 units through this. So now I need to find out how much can I actually send to each of these arcs so that nothing is lost in between, and whatever is sent from S is received at T. So to do this, what we want to find is what is the maximum that we can actually send, right? And through each of these edges, so that finally all these things will reach T. So for this, we define what is called a flow. So flow is basically a function, again a real valued function, which is bounded by bounded below by 0, because I cannot send anything less than 0, right? And which is essentially bounded above by the capacity for each arc, right? But it also should satisfy that for every vertex that we are looking at, whatever comes in must also go out. Basically, the sum of all the incoming flow must be equal to the sum of all the outgoing flows. For every intermediate vertex, we want this, right? So that we make sure that nothing is lost in between. So such an assignment to the edges is called a flow. So a flow in a network, and the underlying digraph D, source S, sink T, and capacity function C is a real valued function f on the arcs of D, such that 0 less than or equal to f of a less than or equal to c of a. Right? The capacity of the arc is an upper bound for every arc in a of D, and f plus of x is equal to f minus of x for every intermediate vertex x of D. So what do I mean by f plus of x? It is basically the sum of all the incoming flows, right? So basically the sum of all f of xy, where y is in the out neighbor, that is the f plus of x, outgoing flows, and f minus of x is the incoming flows, that of all y in n minus of x, right? The in neighbors f of y comma x. So that is basically the f plus x and f max. So if this is equal for every intermediate vertex, and this capacity constraint is holding, then we say such a function is a flow. So here are several examples of flows in the same network. So if you look at the first example, right? Everywhere I put 0, it's a valid flow, right? Because if 0 is coming in and 0 is going out, it's okay, fine, right? It's a real valued function which satisfies this. So there is a 0 flow. So this is called the 0. We want to maximize the thing. So we have to look at other. So here is another example, right? Where the so one is going in, right, and one is going out, and one is coming here also. To u there are two coming in and two is going out. So for u it is okay, and v is the other intermediate vertex. One is coming in, and one is going out. So that is also okay. So for intermediate vertices, this is okay, and then some, and for S and T, of course, it doesn't matter. So therefore, we have a flow here, and here is another flow, right? 2 is coming through this edge, right? This arc, and here it's all 0, and 2 is going out. So this is also a flow, and here is again another function. So 1 is going into V, right? 2 is going out, and 1 is going in here, and then again 1 coming from here. So therefore, that is 2, and here 2 is coming here, and 2 is going here. So this is also fine. So this is also a flow, right? Okay, so we have examples of flows, and I think what time is